So I think we are starting on time. Hello to everybody. Basically, the title of the talk, as you guys already heard it, wants to convey two things. I like to show a broad presentation, so I'm not going to go into very much detail about anything. I like to paint a broad picture of my group it's working on, and to try to interest some of you to work with us or something like that. The two main ideas that are very common to everybody are that, one, we really need to understand what's going on globally, both in terms of trends, tendencies, change, global change, but also in terms of variability, to be able to act locally, to be able to understand what's going on locally, especially in a narrow valley like ours. That's already a very challenging question, but I would say that even more challenging is actually to be able to understand it, to act in risk management and air quality. There's already a multi-scale question hidden in those words that I just said. If we go to the next. I'm going to start just as a motivation to show what's going on in the last 24 or 48 hours with our cloud dynamics. If you go to the next. You could argue many things just by seeing that. I'm not going to, but I'm going to argue that there's a lot of dynamics, multi-scale dynamics that we really need to understand in able to act locally, as I just said. And when I say multi-scale, I really include even the turbulent scales. If we need to understand what's going on in air quality, for example, in this narrow valley, we gotta understand what's going on in the very small turbulent scales in terms of fluxes, because those control what's going on in the boundary layer, and those control what's going on in convection, and then those scales end up controlling what's going on in terms of local precipitation generation, but also in terms of air quality. So here you just saw, if you could click again, some of those interactions that you could argue is that what's going on with Otto in the Caribbean ends up pulling some of the moisture that we had entering into the country through the Amazon. You could argue that. It's been argued many times and with very good proof in some cases. And that ends up, as I said, controlling what's going on here within the valley. Dale la siguiente. Since I'm going to start talking about global climate change a little bit, I just show probably what's been shown many times today here, as is the temperature anomalies, the global trend in temperature anomalies. That is very clear, and we could argue the exact magnitude. There's been debates, different data sets, different instruments, land surface instruments, satellite instruments show different amplitudes of that trend. But that's not the question here today. What is very clear is that there is a trend. There is a trend globally, and if we go locally to it. There was a trend in temperature there locally, and I hope it's the only one, but if not, we'll do something. So the question in temperature is not very interesting. I mean, it's important, but for us, I argue today that it's not very interesting. What is really more important for us is what's going on in the trends in the distribution of precipitation. So if we go and to study precipitation, and before that, we take a look at what our National Climate Center says. To me, this is really interesting. This is the second communication. We're now in the third one. So according to IDEAM, 3 years ago, or 4 years ago, this was published more or less 4 years ago, all the orange areas will be drier than today, more than 30% drier. That's IDEAM 4 years ago, and this is IDEAM now. The blue areas that coincide very much with the orange areas that you just saw according to the IAM, are going to increase in precipitation more than 30%. And a lot of policy was made with the previous plots. And now our National Climate Center is saying we're in the 21st century is going to happen the complete opposite of what they said 4 years ago. Now, these are trends in annual or monthly precipitation. If we go to see that, Julian Urán, in his master thesis, took a closer look to more than 100 gauges, exactly 86 of them, with very long records, very well managed in situ stations. And what he found in terms of annual or monthly trends is that almost all of the stations are like this. This is more than 50 years of data in one rural station, and there's not significant trend at all. This is just one example. If you look in a map, out of 86 stations, 72 of them show no trend at all, not significant trend at all. If you want to look at the non-significant trends, then it's more or less half and half. It's like Hillary, Trump, more or less. 39 show negative trends, 33 show positive trends, but in general, there's no trends at all in terms of the annual or monthly precipitation trends. I don't know where IAM is getting their facts. This is what's going on in terms of precipitation. We haven't had more or less precipitation in our region in the last 50 years. But what we really see is, click enter. What we really see is that if we take a look at the percentiles, and I'm showing here 3 of them, the most intense rainfall events that correspond to percentiles of 70%, 80, 90, 99%, those are really increasing, and they're increasing rapidly. We find evidence in almost all the stations, all registers that we have increasing extreme precipitation events with no increasing or decreasing precipitation cumulatives. And that is very important for local risk management. I'm not here. This plot shows the percentile and the magnitude of the tendency. Still results from Julian Urán's thesis. And you see that if you go to percentile 90, 95, 99, then the percentage that we have in terms of increasing precipitation events is very strong. Again, an important message here is that those trends we only see if we look sub-daily precipitation. We don't see any trends at all when we look at daily precipitation, for example. What we have here is different cumulative periods. So we look at precipitation, we start by adding up all the precipitation within an hour, then 2 hours, then 3 hours, so on and so forth. And all the trends that we see here, when we look at precipitation with a resolution of 1 hour, 2 hours, go away after you start looking at daily precipitation. So if you want to see change in precipitation and you have a daily time series, you're not going to see anything in terms of important changes associated with climate change. All the information in terms of precipitation changes associated with temperature increases are within an hour, within the scale of our precipitation events. We have precipitation events that last more or less 4 hours, stratiform, not very intense, but we have precipitation events that last 45, 2 hours, mostly very convective events, very intense, and those are the ones that are changing. Same stations, same sites as before where we didn't see anything. Now, out of 86, 76 sites show a positive significant trends in all the higher percentiles. And you can see the map there. So if there's something common out of these stations, is that extreme precipitation events are increasing without increasing monthly precipitation. So how can you have that? Well, this is the association with temperature. And then you see for most of the stations that you have both precipitation and temperature records, there's a clear association that follows more or less the Clausius-Clapeyron relationship that if you have higher temperature, then you have a higher chance of having more water vapor in the atmosphere. The question that I was asking is, how can you have more extreme precipitation events without changing the mean of precipitation? And that's because in addition to see more intense events, then you see longer, drier periods in the same scale, of course, as the one that you're looking in the precipitation. So this plot on the left shows that for different periods of accumulation of rainfall, then before the orange plot corresponds to 1996, and the red plot corresponds to 2008 till 2013. Now, in the recent years, you have more periods with longer, drier periods, longer periods without rainfall. So this balances up the fact that you have the same amounts monthly, more extreme precipitation, but longer, drier periods. If you look at models, then Susana Cadavid in her thesis looked out of the 20-something and 40-something CMIP3 and CMIP5 models, only 7 of them really represented the Colombian climatology in a decent way. And when we say a decent way, we just wanted 2 very simple things. We wanted the models in the 20th century to represent the annual cycle of precipitation, very easy. But some models didn't. Some models didn't represent well the transition of the ITCC. And we also wanted that the models at least represent somehow, not in a very strict way, but we wanted some of them to represent the relationship that Colombia's climate have with ENSO, right? And as I said, out of all these 20 and 40-something models, only 6, 7 of them, 5, 6, 7 of them, depending on the criteria, representing well the climatology. If you look at those models and project the future rainfall, and these are percentiles, but percentiles out of monthly precipitation. If you do a probabilistic projection, you see that in none of the percentiles of monthly precipitation in Colombia, you see trends at all. You see basically in the projections what we are seeing in the data, no trends in the monthly precipitation. But if you go and take out of those 6 or 7 models, there's one of them that provides information 3-hourly. So going back to Julian Uran's results, he looked at the intensity, duration, frequency curves that are very common in engineering to see how those curves change associated to climate change. So in this model, this is one of them, CC, CM, CC, CM, whatever, it could be any one of them. This is one of the good ones. This model doesn't show any trends in precipitation monthly, but it shows an increase in a strong increase actually, a strong increase in the IDF curves, which should suggest to us, most of us here engineers, that we should somehow consider this when we are doing our little designs of anything, because intense events, also models, are projecting them to be more frequent. Now, the underlying process, we believe that the underlying process has to do with the fact that there's a big connection between SST and the column integrated heating in the atmosphere. If you actually go and compare those two, you see that there's a big correlation of those. This is globally. Now, there's a big gap. I said, this is my argument, there's a big gap in our understanding. And that big gap is we know what's happening globally, we know what's happening locally, but we cannot connect them yet. If we go, we see that within those areas we have a net increase in atmospheric heating that will provide the energy to have more intense events. We see, and Carolina Cruz, the student, not the model, is working on this very hardly. And she, in addition to the tendencies, is looking at how the location of the column integrated heating changes in the atmosphere. And we have very big changes, for example, from Niño events to Niña events. The location of the heating in the atmosphere changes very significantly. And that will also imply that we can change not only, in this case, the total amount of rainfall, but also the extreme events. And I'll show some of those results later on. Now, locally, we have a couple of instruments that will help us, or that help us to study those extreme events. We have a permanent sounding system, not an actual sounding, but a microwave radiometer that allows us to have the thermodynamic profile of the atmosphere at all times. We have a wind radar, and then we have a precipitation radar. And in the Carlos Cuervo, it's looking at all these typical thermodynamics indices associated with rainfall, and then we see that a lifted index, something that is very simple, but gives us an idea of energy, in the convective energy in the atmosphere. In order for you to have extreme intense events that correspond to the red dots with high cumulative, then you have to really have lower values of lifted index, which means a lot of convection. Above the zero line, then you don't have a chance at all locally to develop intense extreme events. So there's a connection, but there's a big gap. We know what's happening globally, we know what's happening locally, but we cannot translate yet the information from climate models in terms of energy to say, okay, in 2050 we're going to have this number of extreme events per month. This is in terms of convective energy. If we go to the next, then we also see the same in terms of convective inhibition. We cannot form very intense events with high cumulative and high intensity in terms of precipitation when we have lots of convective inhibition. And we are fortunate that here within the valley we have a way to measure convection inhibition all the times. So there's a lot of information for many theses and studies. So this is somehow a connection that still needs to complete. We still need to complete this information in the intermediate scales. How is the process of energy cascading from the global to the local domain? Now, in terms of the spatial structure, in terms of 2 minutes, in terms of the local structure, I was saying before that we have, I have to know what to say now. We have a lot of influence from outside, right? But we have a lot of influence from within our country as well. And topography is one of the main factors. So this is the extreme event that happened in Salgar last year that killed more than 100 people. And we had a strong intensification due to topography. Go to the next. Julian Sepúlveda worked out a way to convert radar information to actually useful precipitation information to hydrology studies. So I'm not going to explain what's going on. He's here, so you can ask him later on. And then, if you click that one, this is the same event, but not in terms of reflectivity, but in terms of cumulative precipitation. So you will see where exactly you had the most intense events. So you need as well to consider what's going on in terms of orographic intensification. And there's a couple of students at the university working on that. Their names will appear and disappear immediately in a couple of seconds. So the purple regions, almost white regions over there, are the regions with more cumulative precipitation and just correspond to a precipitation event intensified due to topography. This picture was before from Google. This is from 2015, previously from the event, before the event. And then if you see the same from Google, don't worry. You will see the areas with landslides. I don't know why it's not showing there. This is what's going on in terms of reflectivity. The event moves from east to west, interacts with topography, and then it intensifies. Really, really intensifies. It's not common to connect, in terms of scales, what's going on in terms of air quality with global climate variability. Usually, this is the Hadley cell, and this is from Camila Angel thesis. A typical Hadley cells when we have precipitation over Colombia, and when we have Niño events, look at the latitude where you have color changes here. So from blue to red, around 8 degrees north, you have the most intense convection. When we have Niño events, these are anomalies, and these colors mean that the center of convection moves south of our country. So this happened this year, in March this year, from February to March. Precipitation in March, if you see precipitation from March 28th to 30 days prior to that date, all the rainfall was very south of our region. We had a lot of clouds, lots of clouds, most of them stratiform clouds, but no rainfall, and that was for an entire month. And then the impact of that in air quality. This is the particulate matter less than 2.5 microns. And this is from 2012 to 2016. You see the big spike there in the contamination locally. And that's, of course, due to emissions. But there was something else acting here to increase that particulate matter in our atmosphere. All the measurement stations within the valley had that spike. And that was due to the ENSO phenomena. This is not working up. So to end, now that I don't have more seconds, my message was, in terms of air quality, that we have also a modulation of air quality conditions within the valley due to the cloud cover variability, because radiative processes are very important for us here in the valley. So any changes in cloudiness end up affecting not only temperature. I mean, temperature, it's very common, and we understand that, but also end up affecting air quality. And we are now, with the equipment that we showed before, the ceilometers, the wind radar, the profiler, the microwave radiometer, measuring all the time the evolution of the height of the boundary layer. So with that information, you can actually make use of it to manage a little bit the problem in air quality that we're having. When we understood and we were able to teach the local authorities about the evolution of the atmospheric boundary layer, there were decisions made in terms of at what times industries could actually pollute the atmosphere. If you have a convective atmosphere, then you could actually do manufacturing processes and emit pollution. There's not still a law about it, but there are volunteering companies that are increasing in numbers in terms of this. And the decisions that are being taken in terms of atmospheric air quality in events that we have very high contamination are based all on technical information related to meteorology. So sorry about the time, and sorry about the, not you, I'm just kidding, about the presentation. Thanks a lot.
Three questions. Do you have more data, historical data, of rain quantity to compare, or just this that you present?
From which source?
Do you have more data, historical data, of the rain quantity?
When I was talking about the trends in intense events, we had more than 50 years of
50
data.
years,
Yeah.
okay.
So that's, the longest that one is going to have, and that's enough. in terms of radar information that is getting used as well to study extreme events, we have now more or less 4 years of data, and we've been learning a lot about orographic intensification of precipitation.
Could you associate this rain extreme event with this climate system? I saw that you said that ITC is more south, of course, but you don't observe the extreme events.
You can see the extreme events from the longer records as well. You cannot, from this study and from any study, you cannot say this exact extreme event was associated to climate change. You can't. But what you can say is that the local atmospheric environment it's more conducive to sustain extreme events. That's why I was going to mentioning the energy, because there's a connection what's happening globally. There's an increase in energy. To translate it to other thing, I can say there's an intensification of the hydrological cycle associated to having more convective energy in the atmosphere. And that's happening globally, but also you see that locally.
And about the climate system, what climate system do you associate these extreme events with? The ITCZ or with ENSO?
No, we were arguing about that with Manuel yesterday, and there's a couple of hypotheses. You can have extreme events in any type of year, even if it's El Niño or La Niña, but you have a higher chance to have them within La Niña years, because all the atmospheric conditions, there's a pre-existing convection, intensified convection over Colombia. When you have El Niño, there's the opposite. You have, if you look at omega, then you see the subsidence in the atmosphere, very, very strong subsidence. But even in those events with strong subsidence, you can have, Salgar event was last year within El Niño conditions. Why? Orographic intensification. You have enough moisture all the time that by itself is not able to form convective events, but then you interact with topography, slopes or changing height more than 1 kilometer in very short space, then you have orographic intensification.
Okay, thank you.
So nice to hear your talk.
Same thing.
Yeah, and especially you connect the global climate changing with local. I think that is really important for public to understand the impact. I have a question. I'm very interested to see you look at the pollution and the rainfall. There's a lot of study talking about how does aerosol influence rainfall. And one hypothesis is aerosol suppress and delay rainfall, but also suppress weaker rainfall and intensify stronger rainfall. So I wonder, as pollution become a bigger and bigger problem here, how would the aerosol influence the rainfall intensity change?
So that question is very nice. We are not still in that stage of the question. There's a first stage, I would say, that we're trying to study, and that's the other effect. What's the rainfall effect in aerosol? Because we have the two-way effect. For the second effect that you were mentioning, we are starting to work with people in this university and other universities in order to also characterize the aerosol. Not only the measurement is enough, but we need to know what the PM 2.5 is made of to be able to know if there's a material that is hygroscopic or not. So that's starting. But in terms of the first event, we have some preliminary results. And I'm going to mention one of them. The short answer is the effect of rainfall on aerosols depends on the diurnal cycle. If you have precipitation events, convective precipitation events from 4 to 6 p.m. During the day, then there's a positive effect in air quality. But if you have rainfall, for example, from 10 a.m. to 3 p.m., you end up reducing the energy that you get in the surface. You end up stabilizing the entire atmosphere, the entire troposphere. So everything that is being emitted during the day, it stays within the valley. The same thing when you have longer stratiform precipitation here within the valley. It starts during the night and usually stops before sunrise. But sometimes it extends till 8 or 9 a.m. And the atmosphere stays stable for longer periods. And in those cases, precipitation is negative in terms of air quality. It helps the accumulation processes of particulate matter. So we're still in that stage of the study. And we've been reading many articles that are coming out from Beijing when they are looking at the effects of aerosols on precipitation and in terms of intensive effects. So they're seeing very nice evidence of intensification in precipitation associated with particulate matter.